Hi everybody, welcome to another video in course Algebra, section 4.5, application of exponential equation and logarithmic equation. So we only focus on exponential growth and exponential decay. At any event, we will have an initial amount and a future amount, and then the exponential term. So where that is exponential growth, where the rate is positive, so it is increasing, or where there it is exponential decay, where the rate is negative, the case is negative, it is decreasing. We still have initial amount, the final amount, and then the exponential term. So first we'll have the exponential growth is increasing. So in this case, we have the initial amount, the future amount, and the rate k is positive. So it is increasing. So exponential growth k is positive. Of course, the t is the time is always positive. So the whole exponent is positive. So that term is, so the function is increasing. So actually we already have this back in section 4.1, the same thing. Initial amount, final amount, and exponential term. So in this case we have it in the form of continuously compounded interest. For that we write in this form though. So you see we have the principal, which is the initial amount, A is the future amount, and instead of we use the rate K, we use R as the rate a year, and T is the time. So pretty much the same formula, but just different letters. Right, now I suppose we have $15,000 is invested, so that is the principal. Compounded continuously, that's why we use this formula. After 3 years, that is the time, and the future value is this. And the question is find the rate. So we have the principal initial amount, 15,000. After 3 years, the future amount will be 19,356.92, and the question asks for the rate. So just put everything we know in this equation. We don't know the rate, but we know that's going to take 3 years to get there, right? So since we solve for R, we need to isolate the exponential term here. Then we can solve for R. So first I will divide 15,000 on both sides. $19,356.92 divided by 15,000, right? I'm going to use all the decimal numbers, but I'm not going to write everything. I'm just going to write 1.29. I'm going to use the whole thing in the calculator, but when I write on the paper, I just want 1.29. 3 times R, 3R. Now, we try to solve for the exponent, a term in the exponent. So exponential equation, pretty much. So we try to get them into the same basis. But we cannot. If we cannot get them to the same base, I will take ln on both sides. So with that, we can take the 3r outside, the exponent outside, and we have ln of 1.29 equal to 3 times r times ln of e. And ln of e is 1. Because ln is a log base e, and base e and base e cancel out, we just have 1. Right, so 3r is equal to that. So r is equal to ln 1.29 divided by 3. ln, I'm just gonna go ahead and copy and paste. Either we do that or we hit second answer, which is the last answer in the calculator. So I'm going to use the whole number, not just 1.29. Once again, if you can do this, go up, highlight the number, hit enter, that copy and paste, divide by 3. And we have 0.08499. So if we round this up, move the decimal 2 places to the right, that looks like 8.5%. So as for the rate, and that looked reasonable. Right. So that's what we have. So compound interest, the same thing as the exponential growth model. We have initial amount, final amount, and the exponential term. Right, next, how long does it take for an account that earns 70% interest compounded continuously to double its values? So once again, we still have A equal to P ERT, that for continuously compound interest. We don't have the initial amount, we don't have the final amount. But what we do know is it's double its values, double an investment. So whatever AP is, the future amount will be twice that. We have the interest rate. And the question asks for how long, so as for t. Right, so that's all we have. So it doesn't matter what the principal is, we're going to double that amount. So I'm going to put 2p in for A. We do know the rate. Right, so once again we solve for the exponential, a term in exponential. So in that case, if we want to solve for a term in the exponent, try to get the exponential term by itself. So instead of divide by the 15,000 here, I just divide by P. So it doesn't matter what it is, we cancel out. I'll just have 2 equal to e to 0.07 t. Right, just like the previous problem, we try to solve for a term in exponent. And we cannot get them to the same base. So I will take ln on both sides. When we do that, we can take the exponent down. And once again, ln of e is 1. So that just cancel out. We have 0.7 t equal to that. So t is equal to Ln of 2 divided by 0.07. Ln of 2 divided by 0.07, and we have 9.9. And this is the time, so that's in years. So about 9.9 years, or round up to 10 years. Right. I just want to point out one important thing here. In finance, here we have what we have in finance is the rule of 70, which is the time that takes to double an investment. Which compound interest, I should say that, but the time for that is 70 divided by the rate. And just want to note here the rate here. It is not in 0.7. It's not a decimal. It is in percent. The rate is in percent. So for this instance, we have 70 divided by the rate, which is 7%. So that's about 10 years. So the time that takes to double investment is, I should say, approximately equal to. So it's not exactly. And we know that continuously compound interest is a little more than just any compound interest. But regardless, it is an approximation. So that's about 10 years. Right. And you say where the 70 come from? Well, if you hit Ln of 2, that's 0.693. So if we write the calculation out, and if we move to decimal place, decimal 2 places to the right, so we have 69.3 divided by 7, which is about 70 divided by 7. Right? So that's how the rule of 70 works. So it's going to take about 10 years to double an investment in this case. So it will double again. It's going to be 10 years. So exponential term will be like this. Originally, we have a principal. It will take 10 years. It will go to 2 times that. It will take another 10 years to double whatever it is 10 years ago. And then in another 10 years, it's going to be 8 times the principal. So every 10 years, it's going to be double in this case. Right. Next, we have the population, which is the same as the compound interest. But in general, it is exponential growth. So on January 1st, in 2000, pretty much the population was 20.8. On 2010, 25.1. And estimated population in 2025. So the reason we have 2000 because approximately we set January 1st, but we do the census every 10 years. And so that's why we have the data usually every 10 years. Right. Now, for every type of exponential growth or exponential decay, I'm going to draw a table like this, just to summarize the data that we have. So in the year of 2000, let that t be 0. So we choose t to be 0 corresponding to 2000. The population was 20.8. In 2010, which means 10 years later, the population was 25.1. And in 2025, which means 25 years later, we don't know the population. Right, so that is the summary of our problem. And exponential growth will be like this. So now I'm just going to use every set of data that we know. First, when t equal to 0, we have 20.8. So I'm just going to write t equal to 0, p equal to 20.8. So we substitute into our problem. 20.8 equal to p sub 0 or p naught e to the k. We don't know k, but we do know the time is 0. Now e k times 0 is still 0, so e to 0 power is 1. So ln of e is 1, so e to 0 powers is e to 0 powers 1. Anything to 0 powers 1. So we have p naught is equal to 20.8. Right, so that's the first set of data. Give us p naught is 20.8. Right. Next. When t equal to 10, the population is 25.1. Right. So we put everything we know. P is 25.1. P naught is 20.8. The rate we don't know, but we know that it's going to take 10 years to get there. Right. Now this similar to what we did previously. Divide by the number. So that gives us 1.2067. I just write a few decimal places on the calculator. I'm using the whole number. And then e to the 10k. Right, once again we solve for the exponent. So we take ln on both sides. That allows us to bring down the exponents. Right, I'll continue over here. ln of 1.2067 equal to 10k. ln of e. ln of e is 1. So once again, that equal to 10k. So to solve for k, we divide by 10. So once again, I'm take ln of the whole number, about 10 decimal places, divide by 10. Right, I'm going to keep this number on the calculator, but I'm just going to write 0.188. Right. We're not going to write the whole decimal places like the calculator. Right. So next, when t equal to 25, what is the population? So once again, we're going to put everything we know in this formula. So we know everything but the population. Initial population is 20.8. K, the rate is 0.188, and the time is going to be 25. Right, so just put everything we know. So we have 20.8, and then times either time or not doesn't matter, but we have, if you use that e, we need the power. Or if we hit second ln, we're just going to enter that exponent times 25. So we use all the decimal places in the calculator. So we have 33.27. 33.27, and that was in millions. Now, the problem is this is a very big assumption. The rate we assume to be about 0.188. By the way, that is not 18%. The rate is actually, if we convert, it's going to be 0.1. Right. Actually, I wrote that wrong here. That should be 0.0188. So that's about 1.8%. So that makes sense. So when you write the answer, when you find the answer, make sure it makes sense. It could make sense if it is 18%. That would be too much. But like I said, I'm just going to write the number. I keep the calculator. The calculator will keep track of all the numbers. So that's why the calculation here is perfectly fine, even though we write here differently. Right? I said to use the calculator to keep track of all the numbers. In that case, what you write there on the paper is not actually important. And at the end, we can only round the answer at the end. So that's about 33.27 minutes. Also, what are the point I tried to make earlier? This is a very big assumption that the rate is about 1.88, the same for every time since 2000. And we know that is not the case. The population increased is not based on, that could be based on the weather, the economy, maybe there's more job here or there, so people move there, so the population, the rate will not be that constant. But in this case, we assume that the rate is 1.88 since 2000. Right. So bottom line is we just have this formula: initial amount, future amount, and then exponential term. What we have next is exponential decay, something that is decreasing, but still the same thing. We have initial amount, future amount, but the rate is going to be negative in this case. Right. I will have a link in the description talking about the half-life here. Pretty much the half-life of any element is the time it takes to reduce to half of its original amount. It's called half-life. I highly recommend that you watch the video that I have the link under the description. We'll talk about half-life, so that will make more sense. Here we just focus on the math. So that's formula. Right. So write the model here remaining, and we use the half-life of carbon-14 is 5,730. So we have Q equal to Q naught e to the negative KT, and this is half-life, meaning that in 5,000 730 years, it will become half of the original amount. So that's what half-life means. Right, so that is easy. Just put everything in here and we find the k. Well, we know the rate k, we know the model. Alright, so we have half of original amount. It will take 5,730 years. Right. So if we divide by Q naught on both sides, we have 0.5. $5,730K. Right. And we know that we need to take ln on both sides. Which allows us to bring down the exponent. So we have ln of 0.5 equal to negative 5,730K. ln of E. ln of E is 1. So from that, divide by negative 5,730, we have K. So we have K equal to ln of 0.5 negative 5,730. Right. Now, I did mention the rule of 70 earlier. The 70 come from ln of 2 is 0.693. So most of the finance, all of the finance students should know that. Now, the half-life is more of the chemistry problem. So all of the chemistry student, I know that ln of 0.5 is negative of that. So all of the reason is, of course, ln of 2, one of them is this, and the other ln of 0.5, which is 1/2, or 2 to negative 1, and you take the negative 1 outside. So that's why ln of 2 and ln of 1.2, I mean ln of 0.5, are just different by the negative sign. So anyway, we have ln of 0.5 divided by negative 5,730. So I'll have that. So just go ahead and write 1.21. But if you're going to, of course, the calculator keep track of the numbers, but I'm going to just say 4 decimal places, 0.968 to make it 7, right? The E means times 10 to the negative 4. So that is a very small number. You say, why is that the rate is positive? Well, the K here is positive, but the rate in general, we have the negative, so we still have the negative. Bottom line is, we have Q equal to Q not E to the negative 1.2097 times 10 to negative 4 times the time t. So write the model, and that's what we have. Right. We have the next part of this problem is that we use the half-life of carbon-14 to date the old material. So, like I said, I highly recommend you watch the video in the description about carbon dating. Right. But from previous problem, we have Q equal to Q naught E to negative 1.2097 times 10 to the negative 4t. Right. By the way, if you want to enter the times 10 to the negative 4, we only enter some number. And then second comma, that gives you the times 10 to the power of. Right. I said even we write that, I still use the calculator to keep track of my calculation numbers. So now suppose that we have in the burial site and we have the carbon-14 is 76.6%. That means it have 0.6766, that's 76.6% of the original amount. So over time, the amount carbon-14 decayed. It's not disappear, but it becomes other element. When it becomes other element, the number of carbon-14, the amount of carbon-14 is decreasing, and it decreases over time into this much, and the time. And the question is, how old is that? How long does it take for an amount of carbon-14 to reduce to 0.766 of it? So this will be simple. We're going to put in 0.766 Q naught. That for the future values is equal to 0.766 of the initial values. And just go ahead, I should just keep this as K. Right? So to get rid of Q naught, divide that on both sides. 0.766. So to solve for exponent, take ln on both sides. So we can take the exponent outside. And we do this many times already. Ln of E is 1. So that's what we have. So T is equal to ln of 0.766 divided by the rate. Right. So I just have ln of 0.766 divided by that number. And we have, oh, I forgot to put the negative. Let's do this again. Ln of 0.766 divided by negative of that number. Right. So we have about 2,203 years. Usually carbon dating around this time is good. If it is more than 15,000 or 20,000 years or later, the carbon dating is not very reliable anymore. Right. So again, pretty much the same model. Now we have a population. But this time the population is decreasing in this form. So an endangered species of fish in that form. The population 6 years ago was 1,600. Today, only 900 alive. When the population below 100, it is irreversible. When will this happen? So I will make a table just like the population we have earlier. Right. So 6 years ago, let that be 0. So 6 years ago was 0. population is 1600. Today, which is 6 years ago, so today is going to be 6 years later than 6 years ago. So if we let 6 years ago be be 0, then today it's going to be 6, and that will be 900. And the question is, when will this happen? Where the population drop down to 100. In that case, it will go extinct because it will be irreversible. So it's just like the population we did earlier. So we're going to use that information. When t equal to 0, the population is 1600. So either we're going to use this, or we use p equal to p naught e to the kt, the same thing. It's just from one formula. It just happened this time it's going to be negative k. The rate k here, if we write like this, the whole thing there should be negative. If we write negative k, then that k there will be positive. Once again, I'm just going to stick with the population model we have earlier. Right, so now we have put everything we know in that formula. 1600 equal to p naught e to the don't know k, but time is 0, e to 0 power is 1. So p naught is 1600. Right. So we use one set of data. Next, use this set. When t equal to 6, the population is 900. So the same formula, 900 equal to 1600, because that's what p naught is. E times k, we know it's going to take 6 years to drop down from 1600 to 900. Here I can divide by 1600 on both sides. So that gives us 9 over 16 equal to e to the 6k. I can check ln on both sides. So that allows us to bring down the exponent. So we have ln of 9 over 16 equal to 6k ln of e, and ln of e is 1. So k is equal to ln of 9 over 16 divided by 6. So we have negative 0.0958 of 96. Like I said, we're going to use the calculator to keep track of our decimal places. So we know the rate. And next is what is t? Where the population dropped down to 100. Right, now we know the population is going to be 100. P naught, we have that earlier, 1600. The rate, the time, we don't know, but that's okay, we solve for it. Now, same routine, get exponential term by itself, divide by 1600. So 1 over 16 equal to e to negative 0.96 t, and take ln on both sides. So that pretty much we have the same routine throughout this section. take the exponent outside. And ln of e is 1. Pretty much the same routine. So time the t equal to ln of that divided by this number. So I will take ln of 1 divided by 16 divided by that number. We have 28.91. So let's round that to 29 years. So just pay attention to one little thing. So we let t to be 6 years ago. So if we want from today, we have to minus 6. So t is in this is 29. Which is 23 years from today. Alright, so that's all we have for this section. So pretty much just have exponential model, whether it is increasing or decreasing, exponential growth or exponential decay. We have the same formula. And what we solve for is we solve for the term in exponent. Take away on both sides, so the routine will be the same for all our problem. As always, thank you for watching. See you in another video in course algebra.